One more thing to talk about for this problem. Look at all of the work above, okay? Our free body diagrams and our equation for the acceleration. You can see the forces acting on the two masses in the acceleration equation. But which force is conspicuously missing? Does that give you an idea about a different way to solve the problem? The tension force does not appear. Right? You don't see any tension force here. So what if we just considered one system, the system of both masses taken together? The tension force is now an internal force, and it is left out of the free body diagram because it consists of an infinite number of action-reaction forces within the string that all cancel out. Only external forces contribute to the motion of a system. Once again, look at the above two free body diagrams and the sketch. The pulley's only purpose is to redirect M1G so it can pull M2 up the incline. Or M1 pulls on M2 with a tension force, okay, right? Because this force here, this tension force, they're both equal because the pulley is massless. And M2 pulls on M1 with the tension force, the same tension force. So what do we call that? That is an action-reaction pair, and tension force is an internal force to the system, so it will not take part in the free body diagram. Since our pulley here is merely redirecting the force M1G, we're going to draw it right over here, right? Whether it's going like this or curving around, it has the same impact on our system to move it in a counterclockwise direction. So we will draw it, and let me get rid of these extraneous pictures here. We will draw it on our free body diagram for the system of both masses, as shown above. One more thing. The forces are all good, but what is the mass of our system of masses, free body, that's represented over here? Well, it is M1 plus M2. So we have to make sure we put that on the right-hand side of Newton's law, the MA part. Once again, we'll start in the y-axis with our forces, and the sum of the forces will be the normal force here. And then, of course, you have the gravitational force pulling it down. We'll say that's equal to 0 because it's not bumping up and down. So the normal force will be M2G cosine theta, just like before. And notice over here, even though we're doing a system of two masses, this only acts on M2. So we just have M2 there for the right-hand side of Newton's law, but as it turns out, it doesn't matter because we're setting it equal to 0 anyway. So then we can calculate our friction force on the system, which is an external force. Friction is pretty typically an external force, and that's mu k normal, and it's mu k M2G cosine theta, and again, it's only acting on this block right here. Let's move over to the x-axis, and we have our force here, M1G, which is accelerating in that direction. We have friction force opposing the motion, and we have the gravitational force, which again is only acting on block 2, and that's M2G sine theta. And here's the key. That's accelerating the entire system, which is M1 plus M2 times A sub x. We then substitute our value in for friction that we found on the previous slide, and we come up with this. Note, there's no tension force present, which is just like when we added the two simultaneous equations for systems 1 and 2 for the first way we solved the problem, when we dealt with two individual free body diagrams. And again, can't emphasize enough, there's an M1 plus M2 naturally present on the right side to represent the total mass of the system. One last notational step is getting rid of AX and just expressing it as A, because the system is only moving in one direction there, that counterclockwise direction, and we come up with A is equal to M1G, that is this block here pulling it down, minus the friction force on M2, which is this, and the gravitational force on M2, which is this, divided by the total mass of the system, which of course is the same answer we got when we used the two systems, one for M1 and one for M2. With more practice with this type of problem and considering the entire system impact, you could observe quicker, hopefully, that the only external forces acting on this system causing the whole system to move in a counterclockwise direction will be m1g, and that's causing you to go counterclockwise, and then opposing that would be the friction force on m2, which you would calculate the normal way with the rotated coordinate system, and then the gravitational force here pulling it down. So as we showed on the previous slide, here's m1 trying to rotate it in a counterclockwise direction. It is being opposed by the frictional force, mu k cosine theta times m2g. Of course, that only acts on m2, that's the block on the incline, minus the gravitational force, m2g sine theta. Again, acting on m2, then your denominator, the total mass of the system, is m1 plus m2. So you can just kind of look at the picture and write all that out.